Hello everyone, and welcome back to my YouTube channel. I'm Yunus Syed, and I'm thrilled to have you along on this journey as we learn the skills needed to become top-notch design verification engineers. If you're new here, I invite you to check out my earlier videos where I dive into the history of SystemVerilog as well as explore sequential and combinational logic. They lay a solid foundation for the topics we cover today. In this video, we're going to explore finite state machines, or FSMs, a fundamental concept in digital design and verification. We'll break down what FSMs are, discuss their importance in designing robust systems, and look at different types like Moore and Mealy machines. I'll guide you through some practical examples and show you how to implement and verify FSMs using SystemVerilog. So, grab your notebook and get ready to dive deep into the world of finite state machines. Let's get started and elevate our design verification skills to the next level. Let's understand what an FSM is. An FSM is a computational model characterized by finite states, a limited number of states in which the system can exist. State transitions, defined rules, or a transition function, that dictate how the system moves from one state to another based on inputs. Inputs and outputs: the machine receives inputs, processes them according to its current state, and may produce outputs. Let's see what are used in an FSM. States. Definition: distinct conditions or configurations that describe the system at any given time. Example: in a traffic light controller, the states might be green, yellow, and red. Input alphabet. Definition: the set of all possible inputs that can affect state transitions. Example: in a vending machine FSM, inputs might include coin insertion, selection buttons, or a cancel command. Transition function. Definition: a rule that defines how the FSM transitions from one state to another based on the current state and input. Example: if the current state is red and the timer input expires, the transition function might move the system to green. Initial state. Definition: the state in which the FSM begins operation. Example: a computer's boot sequence might always start in a reset or initialization state. Output function, optional. Definition: determines the output of the FSM based on the current state, and possibly the input. Example: in a Moore machine, the output depends solely on the current state, whereas in a Mealy machine, the output depends on both the state and the input. Next will be types of FSM. Mainly there are two types: Moore and Mealy. Basically, Moore machine is output based solely on the current state. Simpler design: since outputs change only when the state changes, timing analysis can be easier. And Mealy machine output depends on both the current state and the current input. Responsive design: outputs can change immediately in response to an input without waiting for a state transition. FSMs can be represented in several ways like state diagrams, state tables, flowcharts/pseudocode. In this video we are using state diagrams. Let's start FSM with simple pattern 1011 both in Mealy and Moore machine state diagrams. Here are the state diagrams for Mealy and Moore state diagrams for pattern 1011. Now I will be explaining Mealy FSM non-overlapping. The diagram you see has four states, S0, S1, S2, S3, with labeled transitions of the form input, output. A Mealy machine's output depends on both the current state and the current input. Let's understand the state diagram. S0, reset/initial state. On input equals 0 stay in S0, output equals 0. On input equals 1 go to S1, output equals 0. S1. On input equals 0 stay in S1, output equals 0. On input equals 1 go to S2, output equals 1. S2. On input equals 0 go to S1, output equals 0. On input equals 1 go to S3, output equals 0. S3. On input equals 0 go to S0, output equals 0. On input equals 1 go to S0, output equals 0. Now let's see the code. As you can see the code, let's understand this. State encoding. We define an enumerated type state _t with 4 possible states, S0, S1, S2, and S3. SystemVerilog automatically assigns binary encodings, 00, 01, 10, 11, to these states. Sequential logic, always _ff. Triggered on the rising edge of CLK or when reset is asserted. If reset is high, we force the FSM into the initial state S0. Otherwise, the FSM transitions to whatever next _state is determined by the combinational logic. Combinational logic, always _com. We first set default values for next _state, to remain in the current state, and out, to 0. A case statement checks the current state and input in. For each state in pair, we update next _state and out as per the state diagram. The key difference from a Moore machine is that the output out is assigned inside each transition condition, reflecting the fact that in a Mealy machine, output depends on both the current state and the input. And we are writing if conditions according to the. Keynote to this is the machine resets to a known state, S0, or an intermediate state, S1, such that once a pattern or condition is detected, transition that produces an output equals 1, the machine does not allow immediate overlap of a new detection within the same clock cycle. Essentially, it does not reuse part of the detected pattern as the start of a new detection within the same cycle. And output on transitions in a Mealy FSM, the output is tied to transitions. Here, the only transition that sets out equals 1 is from S1 to S2 on input equals 1. All other transitions output 0. Let's see the test bench. Here is the test bench. In simple words, it generates a clock signal with a period of 10 nanoseconds. Drives reset high initially, then deasserts it, allowing the FSM to start operating. Applies various in values to exercise different transitions in the state diagram. Uses $monitor to print the time, reset, input, current state, and output whenever a signal changes. As you can see in the run area. This example shows how to translate a Mealy machine state diagram into SystemVerilog code. By carefully defining the state transitions and outputs, you ensure that the synthesized circuit or simulated model behaves exactly as specified in the diagram. Always verify your FSM thoroughly with a robust set of test vectors or formal methods to ensure correctness. Please try other state machines. All you have to do is follow the state machines accordingly. Thank you. I hope you understood the FSM, and for next video we are learning full adder and subtractor. Signing off.